Hi, my name is Brian Caffo, and this is the class on residuals, diagnostics and variation in the Coursera regression class, taught by myself, Jeff Fleek, and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so just to remind ourselves of some notation, we specify the linear model this way as the sum of a bunch of linear effects from the covariates multiplied times the parameters. As we need here, we're going to assume that the errors are IID normal 0 sigma squared, and then we define the residuals as we did before. EI, notice there's a difference between EI and epsilon I, right? Epsilon I is the true error, and the EI are the observed residuals, are the difference between the observed data point and the fitted data point, where the fitted data point is merely our regressors, but then multiplied times the fitted beta values. Our estimate of the residual variation is just the average squared residual, where instead of dividing by n, we divide by n minus p for unbiasedness. Okay, so hopefully this none of this is a great stretch. Given everything that we've accomplished in linear regression, none of this should seem so bad. Now, let's look back at the Swiss fertility data. And so you can do data Swiss. And par MFRO C22 just says I want 4 plots arranged in a 2x2 array. I'm going to fit my linear model, and I'm just going to include all my covariates. And I'm just going to say plot fit. And it gives us these set of different plots, and what we're going to talk about today are what these, basically what these plots do and why someone would want to plot them, right? So this is, they're assessing different things, different aspects of model fit. Okay, so let's talk a little bit about outliers and influential points. So consider these 4 orange points here. So this one's easy. It's sort of right in the middle of the data. It probably isn't very influential on the model fit, and it isn't very deviant from the model behavior. Anyway, this guy probably isn't very influential because it's right in the middle of the data cloud, in the middle of the x values, but it is very aberrant relative to the what we kind of perceive to be the model. This guy has a lot of potential for influence in that it's not around the data points at all, the x data points at all. So remember our regression line has to go through that middle x bar, y bar point. So a point out here, has a lot of potential for influence. It's almost like if this was a fulcrum and this is the bar, as you get further out on the bar, it has a lot more force to be able to move the line. So this one has the potential for a lot of influence, but elects not to exert it by fitting in nicely with the model that the rest of the data define. And then this guy is, if we were to have included this guy in the fit, the regression line would move down. This guy is both influential by not being in the data cloud of x's, outlying in the sense that it doesn't seem to appear to fit the model terribly well. Okay. So let's just talk about all these different aspects of what it means to have an outlier of a different sort or an influential point of a different point. So first of all, let me point out, calling a point an outlier is vague. And that's what we're going to talk about today, is diagnosing different kinds of outliers or different kinds of points in the regression model fit. So I can just say outliers can be the result of spurious or real processes. I mean, obviously, if you have an outlier that's just a data entry error, that is a different thing than an outlier that just happens to have a large x value and the model doesn't adhere well out in large x values. Outliers can have varying degrees of influence. They can conform to the regression relationship, i.e. being marginally outlying in x or y, but not outlying given the regression relationship. And then I just go through all those 4 points that we already went through right here, and you can read that yourself.